The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and thank you for joining us on our call today. My name is Christina Spearman from Transcat, and I'll be your moderator this afternoon. Our webinar topic is using a portable bath to improve calibration of sanitary RTDs and transmitters. This topic is being presented by Travis Porter from Fluke Calibration. Travis has worked at Fluke Calibration in American Fork, Utah, in a variety of capacities for the past 21 years, including customer service to technical support. His current role is Inside Sales Account Manager. We expect today's presentation to last roughly 40 minutes, and then we'll answer any questions that have been submitted. During any time during the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Travis.
All right, welcome everyone. As Christine mentioned, we're going to talk about how to use a portable bath to improve sanitary temperature sensor calibrations, and as well as a transmitter calibration, so kind of tie hand in hand. Let me go over here. Oh. Have I got control now?
Yep, you should be good.
Okay, there we go. All right, so let's again, sorry about that. Again, as she mentioned, I've been around about 21 years with Fluke, variety of different positions. Currently, I'm in Inside Sales Account Manager on the sales application side of the fence. All right, so let's get going really quick. There's a lot of options out there for sensor calibrations, as many of you know, for RTDs or PRTs, DUTs. There's a lot of different acronyms out there for these, but basically they're all some sort of a thermometer device. So again, we're going to talk about a few ways. The most conventional ways, is to use a calibration bath in a lab. That's going to get you the best uncertainties in that. And then a lot of folks are moving to dry wells. There's some benefits there, mostly speed and size accommodations, but there's always a trade-off between, best and speed and stability. So again, we've kind of come to the market with these kind of portable baths, kind of a good midpoint to kind of help close that gap on best in a lab versus a dry well. And then we've kind of honed this one specifically for the TriClamp sensors that we'll get into, but it's not only for that. You can do it or use it, I should say, with a variety of different devices. Again, going at this particular application, a lot of folks do it on site. Where you find a lot of these sensors are in various clean rooms on the pharma side or bio type reactors. That said, I've also seen the TriClamp Clover style sensors used in applications like Coca-Cola and Coors Brewery. They've got them anywhere. It's usually used where you're transmitting or moving product to a different area through piping. Some things to consider when you're doing on-site or calibration of these is where you're going to be doing it. So again, typically the folks in the pharma side have their own considerations for the sanitary. That's one consideration we did take into account for the bath. It's a full stainless steel design, can be wiped clean with the sterilizing chemicals that are needed. Other things to be considered in other applications, sometimes these sensors aren't placed in the most convenient areas. So I've had customers that have to sometimes get up on ladders, catwalks, different places. So again, there are some trade-offs where, a dry well may be better versus a bath. So again, that's kind of a application question you would want to discuss with your sales engineer on that. Again, kind of benefit versus risk in the particular application. But again, that's to be considered with all on-site type work. So again, we're talking today mainly about the TriClamp, but again, baths and dry wells can be used for a variety of different sensors, thermocouples. Again, it's not limited to, but again, just bringing it to your attention. Some of the, limitations of using a dry well versus a bath are because of sizing. So again, typically dry wells work best, rule of thumb for your more traditional sheath type probes that are, an 1/8, 3/16, 1/4 inch diameter with, a variety of 6 inches or longer stem lengths. When you get into some of these different thermocouple designs and transmitters and TriClamps, they're usually very short, and so you can't really attain a whole lot of good immersion in a dry well. And again, a dry well's designed to be used typically fully immersed to get the best results during the calibration process. So I keep again referring back to TriClamp, sanitary sensors, or Clover. What that means is it's just the design of it. So we're going to touch on that briefly. Basically, the TriClamp sensors are the ones with these little flanges. The flanges can range in size from a 1/2 inch up to as big as 3 inches. The reason why it's tri on that is there's 3 parts. You've got usually the inlet, the clamp, and then the actual sensor. So again, the 3 pieces, hence TriClamp. But again, I've also seen these called Clover, and then again, sanitary sensors. So again, just kind of digging in a little bit on the explanation of some of the terminology that I'm throwing out there. All right. The things you want to consider with the temperature source is actually, many things. So there's uncertainty that can come from stability, uniformity, repeatability, immersion depth. Different things can cause or influence your overall uncertainty in the process. So in order to get the best calibration, you got to consider what you would be testing in what particular product or heat source. And again, sometimes you give up, some of the benefits of, say, a dry well, some of the speed and cleanliness of no fluids, because you can't, again, say, accommodate there a short sensor. You're just not going to be able to immerse it far enough, and you're probably not going to get the thermal conduction that you need to get a good reading. So again, like with all sensors, the TriClamp sensors vary in lengths and diameter. We've got a few different baths that we've used in the industry over the years that work well. And people have used these as well as some of our standard baths. But again, with this design, we kind of went at the market of improving your throughput. So, having the ability to test more than one at a time, which is the case with some of our smaller micro baths, and again to provide some additional flexibility with immersion depth. And we'll touch on that as we go through this. I've got some slides on some of the features of the bath itself, again, to kind of get the best results in the field from the testing process. So I mentioned again, dry box are somewhat limited. They are, due to the the design around what they typically work best for, which is again the more traditional sheath probes, and then 2, typically due to the size of the inserts or block assemblies, you can only do about 1 again with any dry block, and typically it's going to have to be a TriClamp that's fairly long with the stem length. And again, from that picture, if you recall a few slides back, a lot of these are fairly short, maybe only 2 to 3 inches in length. So again, you kind of run into some potential issues using a dry well. Other folks will use, circulating baths, but again, you're dealing with a large volume there, and again, that's not very ideal if you're going on site. A lot of times these cannot be pulled out for long periods of time in a process. So again, not an ideal solution. So again, that's why we kind of came up with kind of these new 6109, 7109 baths, kind of to improve upon things. So again, historically, our micro baths were pretty good. They're about a 1/4 degree accuracy to the display. The 6109 and 7109, we've kind of improved upon that. They're 0.1 accurate. And these are the first baths that we've really brought to market that fall under our 17025 NAVLAB accreditation. So again, most heat sources, with the exception of a few, are traceable only type calibrations. But again, this one, when the design, we said we need to do one better. So again, we've brought it into the fold of our accredited type of products. So again, the main go at this one was primarily pharma bio type, where it's a sanitary room. So again, hence the stainless design to kind of help with the sterilizing chemicals that have to be used to prevent contamination. All right, we're going to talk about two methods of using these products for calibrating the different sensors. One is where they leave the actual TriClamp connected to the system, or the control room is what some folks will call it. The second we'll discuss, disconnecting it. And there's actually kind of twofold on the disconnected one. We're going to talk about a sensor, and then also a transmitter, like a 4 to 20 milliamp. So again, the process is very similar. It's just how you kind of interpret the data, or how you've set up the testing. But again, we're going to explore that in more detail as we go through. Again, there's advantages and disadvantages to both. So again, if you're looking to get information on this, have a good discussion with your sales engineer on that, of everything that may or may not be a concern. All right, so we're moving into the example one of using just the bath with a connected, or what they call a loop calibration test. We're going to state for this that we're going to use the TriClamp sensor. We're going to pull it out of the process that it's in, and we're going to test it at 3 points, say 0, 70, and 140 in the bath, but we're going to leave it connected to the control loop at the control board. So again, we're not removing it completely, just from the pipe that that's at. So to kind of set this up, these are kind of some of the new features we've kind of come up with for the bath. So again, there's an internal holding fixture. And what this is going to allow you to do, depending upon size, is adjust the depth. So again, if you look at the picture on the right there, you can actually get 4 sensors in the tank with a reference probe if needed. And those flanges on that one, I believe, are 2-inch round. So again, you can get quite a few more versus one at a time. So again, if downtime is a concern, this is a really good setup here. Also, in the size previously, we showed how some of these sensors are very short, 3-4 inches on the stem lengths, maybe even shorter. The probe holding fixture there, again, allows you to actually kind of seat them down further from the top of the bath and hold them in the fluid. So again, this can help with getting better immersion, because again, you do want to kind of have the flange itself actually kind of right at the fluid level to help reduce any stem conduction or errors that are going to be contributed by ambient type conditions. So again, this is kind of showing a very basic physical setup of that, and then we'll keep talking through it. All right, the next piece of the test would be to set up your set points, and you can set these up manually, but the units themselves have built-in programs. They're pretty nice in that you can define several different test points, soak times, and a variety of ramp soak type options. So again, this can help with someone if they're doing multiple tasks on a job. Again, so in our example, we're just kind of saying we're going to test with 3 points with a dwell time of 20 minutes at each point, and then move to the next. So what's going to happen is we're going to program the bath to 0 in the bath program. Then it will come up, stabilize, soak for the 20, and then move to that 70 point. This could also be helpful too if it's a single person doing the job where he's having to move from the actual point of test at the TriClamp sensor, and then having to move back to the control room to view the results. So again, it can allow you some time to move back and forth, and again, still have some semi automation of the process. All right. So I didn't go through kind of the ins and outs of setting up the entire process, but again, we're going to assume that we've already got that pre-programmed. We're going to select our program 1 key, which is going to be the pre-selected program that we've determined to run to those 3 points, and we're going to tell it to go to this. So once that's enabled and goes, you're going to see the bath kind of come up, kick on. You're going to see the cooling power come up, and the bath will start to cool to that first set point of 0. You can also watch the bath, as it's coming down to temp. The other thing that's really nice about these is when you're setting up those program limits, you can actually set a stability and set point limit. So the bath won't start the soaking process basically until it's reached those stability limits, and then the timer will begin to count. This is pretty useful, again, if you've got, say, one person doing multiple tasks on a job. Kind of helps semi-automate it, kind of to free up some of their time. All right, so we're just continuing the process. Again, if you're curious about some of the features, we've got a few buttons where you can view a graph or the recording that's going on or the statistics. But there's also a ready light on our new unit. So again, when things have come up and things are ready to start the data collection, or for the person to manually start grabbing the data from the bath, the light does go green on that. So that, again, just a very good visual indicator to kind of, again, help free up time. I think there's also audio controls where the unit will beep at you as well. So multiple ways to kind of say, hey, this is ready to go. You can begin your testing process. We're ready to take some data now. So again, in this, we're just kind of saying we've come up to the temp now. We've fully stabilized to the limit that we've set. And now the bath's saying, okay, I'm ready. And the light has turned green. So again, really good as kind of semi-automated if you've got a technician who's kind of running a one-man show on site. So now that we're starting to record the data, so again, you're just going to have to do this either, again, manually. There are ways to, again, we've semi-automated it, but for the actual data collection, since we've left that sensor in place, the only place we can really see what it's reading now is back at the control point. So again, we'll assume that the unit has now come to 0. It's stabilized. We look at our bath setting. It says I'm at 0. We know that the uncertainty for it's plus or minus 0.1. And then we can walk back to that control room and see if we're within the spec that we need to be. And again, too, typically for these, with the 0.1 accuracy, you're going to be testing sensors with a larger uncertainty, maybe potentially plus minus 1 or even plus minus 0.5. Again, most of the time in a process, you're carrying some sort of a test uncertainty ratio. And it's usually in the industry, the rule of thumb is 4 to 1. So again, something to keep in mind there. Again, on your uncertainty, but again, there are many methods, whether you're doing right to a display or using a reference, there's a couple of ways to go at it. All right, so in the next few slides, we're going to talk about that second one where we've actually pulled the entire sensor itself out of the process. So at this point, it kind of changes things up because we're no longer using the control room as kind of the verification on the other side for the readout. Couple of benefits to this is dependent. A lot of times folks will then perform a calibration on the control panel itself where they source, various resistances or say millivoltages if you're using a thermocouple to the board itself to kind of validate that it's also performing. And then you can kind of take the sensor and test it on its own. And the reason this is kind of a more enhanced or a good method is because you can kind of pick apart what may be causing potential error in the system, whether it's coming from the sensor itself or if we've got maybe a potential component issue on the control board. So again, this is where we kind of dig into a little more robustness, and this is where we can you can start digging in pretty hard, depending upon how you're going to analyze the data that you're getting from it. In kind of that first example, we were kind of just assuming we were doing a quick calibration of comparing temperature to temperature. With some of these new methods where you're pulling the unit completely out, again, depending upon the controller interface, there may be some potential there to input various coefficients to correct for, say, sensor drift, and that could be on the RTD or the control board side of the fence. So again, in this example, we've pulled the sensor completely out. We've now hooked in a reference probe as well as the device under test 2. We've pulled in now a third piece of equipment, which we're going to use our 1586A. And then we've also connected that to the 7109 or 6109 bath, whatever one you would be doing. In this particular example, all the setup is mostly done from the 1586A point of view. Now, while the 6109, 7109 baths have capability to have their own internal programming and menus, we're using the 1586 now as the driver. So that's a nice feature about the 1586A. It does have pre-programming as well set up, which not only allows you to drive a heat source, but also to log not only the reference thermometer, but also the devices under test that you're testing. So in this, we've got that set up. I haven't dug in too far as far as setting this up. If you're curious about more on the automation using the 1586, you can go to our website. We've got several videos on that. They would be much more benefit as far as viewing to give you an idea what's involved in setting that up. But again, it's not very difficult, and again allows some automation there again to free up a tech's time. So once we've got everything kind of set up and determined and programmed, basically you're just going to start the test again. All right, so this is kind of a few points here that I talked through, and we're going into that. And again, this is where the video will make a little more sense on what is all done setting up this. So this is just running through a variety of menus of the trigger, start, scan, recording, different things as far as how the testing is going to go through. All right. So once it kind of starts, it's monitoring moving through, and then once it concludes, you've got this big group of data now. So again, the 1586 has a built-in USB. So once everything's ran, you can basically export the files from the testing in the CSV format to this thumb drive, and then you can take it over and use some other database, maybe Excel or something, to kind of analyze the data of what's gone on during the testing process. So again, this is where things can get a little more involved. Example, if you're using, say, an RTD, and you've now got just raw resistance data compared to, say, temperature data of the standard, and you're going to recalculate, say, the calendar Van Dusen coefficient for the probe and then plug that back into the system. This is where you would take that raw data and kind of run the additional mathematics that are needed to fit the raw data. In this case, it would be resistance data to the temperature. So again, automated, semi-automates the whole process. So with the exception of kind of the tweak at the end that, during the testing, that's something you probably want to review anyway, just to ensure that there's no skews that looks off in your data. no spikes or anomalies that you may want to question, and potentially maybe rerun a test on the particular sensor you might be seeing an issue with. All right, so continuing on with this method 2 type system where we're now kind of integrated a readout device like the 1586, we'll kind of show you how to use a temperature transmitter. The process is fairly the same, only instead of now outputting the resistance or millivoltage, the transmitters typically output a 4 to 20 milliamp signal that's interpreted. So basically, if you're say using a 0 to 100 probe, 0 would be considered 4 millivolts and 100 would be considered 20 millivolts. And so the calibration kind of relays that signal versus the actual resistance signal of the probe, which may be 100 ohms at 0 and then 140 or whatever it is up at 100. So again, a little bit different. The reason a lot of folks do that is you can transmit the 4 to 20 milliamp signal much further than you can a resistance signal. So again, that's why most of these are used in much larger plants that are, say transmitting over, hundreds or thousands of feet. So we're going to kind of show you a demonstration here of an option that if you go with the 7109-P model, which is called a process option, kind of builds in some additional features to the unit. So in the first example, we kind of showed the bath had its own capability to kind of run some programming. Now with this additional feature, you can also have the option to run in a reference probe, as well as here you can see the milliamp loop. So you can actually source to the transmitter and kind of get a reading as well. So again, if we were to set this bath at 0, run it down and connect up the sensor itself, we would see that it would be outputting 0 versus 100 ohms, and then 135-ish, 40 ohms at 100. So again, just a different way to kind of isolate that transmitter and kind of do a good test. Again, here we made again reference to the reference probe versus the immersion depth of the sensor. Again, you never want to have your sensors that you're testing touching the actual bath. You want the fluid to kind of circulate around them. And then too, just in general, a good rule of thumb on any sensor testing is usually 20 times the diameter plus the lengths of the sensor. If you don't know the sensor length, or if it's a thermocouple, typically you can stick with just 20 times the diameter. So again, typically if you run the math out, a 1/4 inch probe roughly comes up to about 5.5, 6 inches of immersion. And what this does is basically, once you get that much immersion, you reduce what they call stem conduction, where your probe basically is conducting ambient air or heat sinking. It's usually more apparent if you're testing to very hot or very cold extremes, because then you've got this ambient metal piece that is acting as a cooling heat sink or a heating heat sink, depending on which direction you're going. All right, so this is just pretty basic. We're inputting the reference probe. The other nice part about this process option is it utilizes what we call our InfoCon technology. So the actual connector for the reference has an IC in it that's programmed with the probe constants. So once you connect it, it self-recognizes, so you don't have to do additional programming like you do in some of the readouts. The next step would be then to take some leads, connect to the loop COM ports, and then on that little transmitter head, typically you just unscrew that. There's a few connection points in there, and you would connect to the 2 outputs for the circuit. Again, pretty basic there if you've done this. Again, when you open up those transmitter heads, there's usually 2 connections for the internal and then the other 2 connections for the outputted. sensor that's going to go to the control board. All right, here's where we kind of go into the bath. You turn on the loop power in the kind of process option setting, as well as activate your reference probe. And then in this example, they said, adjust to each of the different set points. You can do that as well, or again, you could run the pre-programmed points again of, say, a previous program if you do the same one over and over. So again, it would go to your test point, ramp up, stabilize, soak. That'll give you some time to gather the data. And then again, once it's kind of gone past that soak point, it'll again continue on and continue to ramp through the various testing points. So again, that's a couple of really quick methods that to kind of use this bath with the sanitary sensors, or any different PRTs or thermocouples, or even the transmitters if we just discussed, to kind of do a cal. Again, there's a lot of other applications these can be used for. I know we've kind of discussed the majority of these being used for the sanitary type sensors, but they can also be, again, used for any type of sensors where the sizing is appropriate. Sometimes if you have very long, say 15, 20-inch probes, you may need a bath that's deeper to kind of negate that stem conduction. But again, this is one of the better kind of portable baths we've gone to gone to market with. You can see here on the next slide, both of the display accuracy is 0.1 across the full range. They're very quick. So again, we've tried to improve upon the heating and cooling time. Because again, typically with a traditional lab bath, with larger volumes of fluid, you're looking at sometimes hours between different set points, depending upon the type of bath. But again, that's kind of going from the best solution to a better solution. So again, also you can see the uniformity specs there are very good, and repeatability is also really good. And again, once we reach temperature in these, again, the settling time, again, to get really, really good stability is about 10-15 minutes on each of them. So again, hope that was useful on as far as going through. One plug here on something new Fluke just launched that I wanted to let everybody know about is called Cubit. So basically, this is a new project we're working on. It's basically an open repository of just cal sheets. So basically, we're trying to get our hands on everything that's potentially calibratable out there in the world, and kind of come up with specs and profiles of the devices to kind of save technicians time. So basically, you can sign up for free. It's no fee or anything, and we've got basically a lot of metrologists loading thousands of devices every week. So we're again trying to make a new open platform, just to kind of be kind of the go-to in the metrology world. So again, I encourage you guys to kind of go check that out. Again, it's free. It's just www.cubit.io. You just sign up, and then it allows you access. Other than that, I guess we'll move to the questions that may have come through during the presentation. So I hope you've enjoyed that, and hopefully we can answer these questions.
All right, thanks, Travis. That concludes our presentation portion of the webinar. We'll now move on to the question and answer session. Just as a reminder, if you'd like to ask a question, you can send it through the question box in your webinar controls. Let's get to our first question. What is the minimum time recommended to keep the probe inside bath fluid, and to take a decision whether or not the probe is okay to take out?
Okay, so we're talking about settling time.
Yeah.
So that depends. So it's usually quicker if you have the probe already immersed and it kind of ramps down or stabilizes with the heat source. What you need to do there is just kind of watch your readings. And again, what you're going to see if, say, you have the heat source already at temperature and you've got an ambient sensor and you put that in, you're going to need to watch that sensor kind of come down and then kind of level out. And a lot of times folks will use kind of a standard deviation to kind of watch that as the data kind of keeps pulling down. Once that curve kind of flattens out, that's when they'll start taking the data. And usually you want to watch that data. Again, with our stability times, again, when we say the bath has come to temperature, you usually want to let it stay at temperature for 10 to 15 minutes, and then you're really solid as far as your stability.
Okay. The next question is related to that. If the probe is a 0 to 140 C temperature and the filled process temp is not more than 90, do you need to test the probe also at 140, or can you test it only at 120 and say that it's okay?
That's a tricky question. Typically, if you're using a probe full range, you should test it full range. Ideally or mathematically, in theory, the sensors should drift linearly. That said, I've seen them do odd things at both the extremes. So I've seen probes that'll come up very linearly to a certain point and then dip. So again, it is best practice to test full range of whatever the range is that it's being used over.
Okay. The next one, how do you calibrate temperature sensors that are not 4 and 20 milliamp like RTDs and thermocouples?
So there's a few ways to do those. That one's kind of a longer discussion. So there's several ways to kind of interpret the sensor data. So most thermocouples output a millivoltage, and most RTD sensors output a resistance. So there's many ways to interpret that. For the thermocouple side, usually Nest, if you look up there, they've got their standard kind of specs of what a thermocouple based on the type should output at different temperatures. And then there's also deviation functions that you can apply to correct those. Same theory on a RTD, it just kind of depends on how accurate you're going to calibrate that RTD. So you'll notice that a lot of times you'll see a DIN class RTD. That one's kind of a very generic window, and you'll notice that the specs on a DIN class RTD are fairly wide, usually about a half a degree or so, depending upon the range. But as you go through different methods of interpreting that data, say from a DIN class to a calendar Van Dusen equation to an ITS 90, basically you're really narrowing in on that window of uncertainty. And those different types of calibrations allow you to kind of narrow in on the band of what the uncertainty can be achieved for the calibration and the probe.
Okay, next one. Do I have to use a bath if my sensor is shorter, like 1 to 2 inches?
Ideally, yes. Again, when we went through the presentation, most dry wells, the shortest ones I've seen are about 4 inches. So if you're running a 2-inch sensor, you're only going to be immersed into that well about halfway, and so the control sensor in a dry well is coming bottom up. And so ideally, what you're trying to do is align those like lining up side by side. And the other thing with the dry well, all dry wells, they have an inherent gradient bottom to top. So if you're only partially immersed, you're going to have this gradient gap between the control sensor and your device under test. So again, a bath works well there. Sometimes when you cannot use a bath, the option is to then get a reference probe and immerse it also at the same depth. But again, you're going to have to find a fairly small diameter reference probe due to that short device under test length.
Okay, do you have to use silicone oils in the bath only, or can you use water?
So the baths themselves are made with stainless steel tanks, so you can use a variety of fluid. And a lot of times the baths themselves have a capable range that exceed different fluid types. So basically, depending upon whatever fluid you're using, you're going to be limited to the fluid's capability, not so much the baths. So the silicone oils in that allow you a much broader hot and cold type span. With our 5012 oil, as an example, that silicone fluid is usable from -30 to about just over 200 C.
Okay, and then it looks like we have one more. This says it's more of a question about baths as equipment. I always have problems with the power pack of my bath. I've lost 2 baths in 2 years.
Okay, so I'm not sure what you're referencing to as the power pack in the bath. I don't know if it's the fuses or the power switching board or the power entry module. That one would be something we'd probably want to take offline and be more specific to get our technical support guys involved if it's a Fluke product.
All right, that looks like it is all for now. So that concludes our time today. If you have any further questions or would like to find out more about Transcat's product and service offerings, please contact us at 800-828-1470 or on the web at transcat.com. Thank you all for joining us today. We hope you got something out of today's presentation and that you continue to join us for future Transcat e-learning webinars. Thank you, Travis.
Thanks. Bye-bye.
Bye-bye.